Okay, our aim in this video is to slightly extend the right-angled triangle definitions of sine and cosine to allow for obtuse angles, with the eventual goal of using trigonometry in all non-right-angled triangles, which could well contain these obtuse angles. So imagine this line here is the ground, and we place a number line on this ground going from -1 to 1. To best simulate the in-class experience, we're going to stick a frog on the end of a 1 meter long pole here on the far right. And this is where we will start measuring our angles from. Then, keeping the left side of the pole firmly planted at 0, we can imagine swinging this frog all the way to the left in a circular arc like that. But remember, we're choosing to start back at the far right. So say we start there and we swing it, stopping at some point here. Then right now we've swung to the left by 50 degrees, say. Okay, so here's what sine and cosine of 50 degrees actually mean. Sine is a machine that actually just tracks the height of the frog here. Okay, the length of this dashed green line. If you want to check, you can quite easily work through the right-angled triangle we've just formed, noting our pole is exactly 1 meter long, and that the green dashed line is opposite the 50-degree angle. So right now, we can say sine 50 degrees is 0.766. The frog is something like 0.766 meters above ground. And no matter what angle we swing the frog by, that is what sine keeps track of. It's a machine whose job is to tell you the height of the frog above ground. So what does cosine do? What we're going to do is imagine the frog now chucks a dump straight down onto the ground, and the poop will land somewhere on the number line. And that number is exactly what cosine of 50 degrees tells you. And again, you can quite easily confirm this one by noticing the length from 0 to the poop is the adjacent side to the 50-degree angle, and also remembering that the pole is again exactly 1 meter long. So right now we can say cosine 50 degrees is 0.643. Okay, when the frog chucks a dump straight down, it lands on the number 0.643 on the number line. So no matter what angle we swing the frog by, that is what the cosine machine keeps track of. It's a machine whose job is to tell you where the poop would land if the frog chucks a dump straight onto the ground. So that lets us easily extend our sine and cosine machines to make sense of obtuse angles. Okay, it's absolutely possible to swing across all the way to an obtuse angle like 120 degrees here. Okay, at which point sine 120 degrees is 0.866, meaning the frog is about 0.866 meters above ground right now. And cosine of 120 degrees is exactly -0.5, because if the frog were to chuck a dump at this point, it would land exactly on the -0.5 mark on the number line. But if we come back to our 50-degree angle point here, this new access to obtuse angles actually leads to some symmetries that pop up. So we could well take this whole right-angled triangle here and flip it to the other side. And before we explore these symmetries, what angle does that side correspond to? See, we're insisting on swinging our pole up from the right, so the easiest way to calculate this new angle is to swing the whole 180 degrees to the left side, and then to go backwards by 50 degrees. So we subtract 50 degrees to arrive at the angle of 130 degrees. Now notice the frog is the exact same height as when we had only swung 50 degrees. That's because it's literally the same triangle, just on the other side, so there's no reason his height should be any different. So you can confirm on a calculator if you want, but the sine of 130 degrees will be the exact same 0.766 as the sine of 50 degrees. But what about the cosine? Well, if we look at where the first poop landed, we see that the length here is 0.643. And by symmetry, it must be the same length on the other side, going to the current position of the poop, but we can see that now it's on the left side, which means that the cosine of 130 degrees is negative 0.643. The number is sort of the same, but now it's just gone negative. Okay, again, you can check on your calculator if you like. So that's the symmetry that comes from swinging the frog around. No matter what angle we swing the frog to, you can imagine the same triangle being built on the other side. And we can always arrive at that angle by swinging the full 180 degrees to the left and then going backwards, so subtracting whatever original angle we had. So here, 180 minus 35 is 145 degrees. Then this symmetry affects the sine and cosine machines in different ways. Because the frog is at the same height either way, then sine of that angle, so 35 degrees in this case, would exactly equal the sine of 180 minus that angle. Okay, so 180 minus 35 being 145 degrees in this case. So in general, sine of 180 minus theta is the same as sine theta itself. Then for cosine, the number on the number line here is what cosine measures, and for the poop on the other side, it's the same number, just pointing to the left. So whatever angle we started with, again 35 degrees in this case, okay, cosine of 180 minus that angle, so 145 degrees now, should be the same number, just negative. So in general, cosine of 180 minus theta is sort of the same number as cosine theta, just turned negative. Okay, so honestly, in this course, we're almost always going to just be using our calculators anyway, so how does understanding this whole story actually help us? Well, it's true that if we need the sine or cosine of some obtuse angle, our calculators are well able to handle that for us. Okay, it's actually when we go backwards that we need to be a little bit more careful. See, the fact that cosine goes negative is actually kind of convenient. It means if somehow we're working on a triangle of some sort and we encounter something like cos theta equals negative 0.819, and we'd want to work out theta itself, okay, we'd do this by applying the backwards machine, the cos negative 1 thing, okay? We'd apply that to our decimal. But see, in this frog situation we've created, right, there's only one possibility for our angle. Okay, for the poop to land on a negative number like negative 0.819, we must swing all the way to an obtuse angle. So you can check that if you just punch the shift cos negative 0.819 thing into your calculator, the obtuse angle 145 just pops right out and you're done. Okay, that's sort of the easy case. But if in the wild you encounter something like sine theta equals 0.574, then see there are actually two possibilities for the angle in our frog story. We could either have swung 35 degrees, or we could have swung the whole 145 degrees and actually both of them would have worked. Both would have achieved the same height of 0.574. But here's the tricky thing. If we punch the shift sine 0.574 thing into our calculator, it only tells us the first answer it sees, and that's the 35 degrees. It doesn't tell you about the 145 at all. And that means if we somehow know that theta is meant to be obtuse, and most likely the question either explicitly tells you or the picture sort of forces it to be, then the calculator will not directly tell you the angle you're looking for. Okay, you have to take an extra step to swing the whole 180 degrees and then to go backwards by 35 degrees. Okay, and so you need to manually do 180 minus your initial answer. And only then would you get the 145 degrees you're looking for. So that's the moral of this whole story. If you know that an angle is obtuse, then cosine is pretty well behaved. But because sine ends up with two options, and your calculator will only ever tell you the acute answer, you must manually do 180 minus that answer to get the obtuse angle you need. Okay, so that's all for this one. Thanks for watching. See you next time.